Welcome back, class. So we're going to continue with chapter 4, section 4.3. So problem solving in the pharmacy is our chapter objectives. We are going to calculate drug doses using the ratio proportion and dimensional analysis method. So problem solving in pharmacy. Using the ratio proportion method to solve story problems. So in pharmacy, we're going to use a lot of story problems. There's going to be a prescription written by a provider, and he's going to tell you a story, basically telling you the story of the patient needs this, and you need to fill it. And by whatever he doses to the patient, you have to look what you have in your pharmacy and be able to use the mathematics of converting whatever the physician ordered and converting to whatever you have in stock in your pharmacy. So if there's a medication that it's 25 milligram doses, and the medication that you have on stock is just 12.5 milligrams, you have to calculate the saying, okay, so I'm going to have to give the patient 2 tablets of the 12.5 milligrams in order to get that 25 milligram dose that the physician ordered. So basically, that's how the problem solving is. So now you will use ratios and proportion mathematically to compare a readily available product consisting of an active ingredient and a vehicle to a desired prescribed dose. A vehicle is an inert, so it's a chemically inactive medium such as a syrup in which a medication is administered. So that vehicle can just be fillers in a tablet. Like we stated here, it's the syrup, but the medication is added to that syrup. So things like that. So it's just a vehicle as into where you're going to, in which you're going to administer that medication. So like the available products, the desired dosage will consist of an active ingredient and a vehicle. So the active ingredient is desired over the vehicle desired. And that should equal the active ingredient on hand over the vehicle on hand. Okay, so this is our ratio and some proportion. So again, our units of measure are going to be the same on the top or in the numerator. And our units of measure in the denominator are going to be the same. So keep in mind that the ratios on the two sides of the equation may be inverted. That is, the vehicle may be in the numerator and the active ingredient may be in the denominator. However, the same units must appear in both the numerator and the same units must appear in both denominators. So that's our ratios and proportions. You can use the steps outlined in table 4.5 as a basis for solving story problems or dose calculations using the ratio proportion method. Usually, you can use the following equation to solve a story problem. So the desired amount of medication over the prescriber's order is equal to the ratio of pharmacy stock. Okay, so next step. Read through the entire problem and identify what the equation is asking for. This unknown amount becomes the variable x, labeled with the unit you are looking for, such as x milligrams or x mLs. Step 2. Identify the prescriber's orders. Circle the dose ordered by the physician. Step 3. Identify the appropriate stock available in the pharmacy, the ratio of pharmacy stocks, such as 1 milligram tablet or 125 milligrams per 5 ml. Should be found on the labels of the drugs used in the pharmacy. Underline this information. Step 4. Identify extraneous information. It is often helpful to draw a single line through any information you identify as not needed. This prevents you from using that information in your steps. Use a pencil in case you need that information again. 5. Estimate what your answer should be. Compare the order's dose to what is on hand. Will the dose be larger or smaller than the dose unit given? Step 6. Use the ratio proportion method to solve for x. When using the ratio proportion method to solve the problem, place the prescriber's order dosage on the left side of the proportion and the pharmacy on-hand ratio on the right side. Round your answer appropriately. Weights are typically rounded to the nearest milligram, and volumes are typically rounded to the nearest tenth of a milliliter. So here's an example. A physician has ordered 10 milliliters of amoxicillin to be given to a child 3 times daily for 7 days. Amoxicillin is available in 150 ml bottles with a dose strength of 250 milligrams per 5 ml. How many milligrams will the child get at each dose? Okay, so again, look at the problem, look at what it's asking for, find what information you need to solve this problem. So, okay, the unknown is X milligrams. The prescriber amount is 10 mLs. The pharmacy has 250 milligrams per 5 ml. Extraneous information include 3 times daily for 7 days, and the size of the amoxicillin bottle of 150 mLs. That information we don't care for. So the answer will be greater than 250 milligrams because there's 10 mLs. So this is our estimate, right? So let's set up a ratios and proportion method to solve for X milligrams. So X milligrams over 10 mLs is equal to 250 milligrams per 5 mLs. Okay, so this is what the pharmacy has in stock. This is the desired amount over the amount that the physician prescribed, correct? So cross multiply, 5 times X is 5X is equal to 250 times 10 ml divided by 5 gives us 500 milligrams. So there's no need to round since our number is already in the correct decimal answer. So using dimensional analysis to calculate the dose. So just as using dimensional analysis method to convert your metric units learned earlier in this chapter, you can now use it to solve medication doses by converting a dose from milligrams to tablets or from milligrams to milliliters. You accomplish this by multiplying the doses ordered by the ratio for the on-hand product. As in the metric conversion practiced earlier, you set up the ratios so that the units of the given dose and the units in the denominator cancel out. When using the dimensional analysis method to solve drug dosage problems, you can still use the steps in Table 4.5 to analyze the information. The only difference is in the setup in Step 6. Dimensional analysis methods tends to use more frequently for simple dosage calculations such as number of tablets. So let's go over an example. A physician has ordered a 25 milligram dose of hydrochlorothiazide. You have 100 count bottle of 50 milligram tablets. What will you prepare to fill the order? Okay, so let's see. What our information that we don't need is the 100 count. Okay, let's go over the steps. So the unknown is X tablets. The prescribed amount is 25. The pharmacy has 50 milligram tablets. The extraneous information is the 100 count bottle. Your answer will be less than 1 tablet because we're going from a greater dosage to a smaller. So let's use dimensional analysis to convert the units. So remember, in dimensional analysis, you want to cancel your units. So if you have 25 milligrams, in our next set of problem, we have to have milligrams as the denominator. So 1 tablet is equal to 50 milligrams. That way our milligrams cancel. So 25 times 1 divided by 50 gives us 0.5 tablets. And that's our answer, so there's no need for rounding. Okay? And that concludes this section. Let's go ahead and move into some of the problems. Let's see. So let's move on to page 109 and work on problem, I think number 1. Let me go get my notes. Okay, so number 1 says, a patient has a prescription order for 30 milligrams of a medication. The pharmacy container of 7.5 milligrams tablet. How many tablets will the patient need? So let's go over our steps. So step 1, we want to know X milligrams, because how many, X tablets. See, it's good to read the problem. How many tablets? So X tablets. Step 2. The order is for 30 milligrams. Step 3. The pharmacy has 7.5 milligrams tablet. I don't see any information that we don't need. I already forgot this. Oh, our approximate answers. So we're going from let's see. So we have 7.5 milligram to 1. So we're going from a smaller to a greater number. So our number should be greater than 1 tablet, right? And then let's set up our problem. So let me go ahead and erase this. I don't have that much steps. Okay, so we have oops, 30 milligram, and we want to know X tablets is equal to what we have in the pharmacy, 7.5 milligrams per 1 tablet. Okay, so now let's cross multiply. 7.5x is equal to 30 divided by 7.5. So x is equal to 4 tablets. Okay, so that's the answer for number 1. Let's go ahead and do number 3. Okay, so a patient is prescribed 125 milligrams of carbamazepine suspension. The label provided has the medication the pharmacy has in stock. How many milliliters will be prepared for this patient? And let me see if I can show you the label. Let me go to the ebook. Okay, so we're doing number 3 right here. Let's see. Okay. So right here's the carbamazepine label. So it says there is a suspension is 100 milligrams per 5 mLs. Okay, so let's go back to the whiteboard. Okay. Oh, erased our stuff. Darn it. Okay, but anyways, so information that we want to know is X milliliters, right? And then we want to, hold on. Sorry about that. So we want to know X milliliters. Doctor ordered 125 milligrams. And we learned that in the pharmacy, we have available 100 milligrams per 5 mLs. So that's all the information that we need. So we can set up our problem. Okay? So X mLs is what we desired over what the doctor ordered, 125 milligrams, set up to what the pharmacy has available. So remember, our numerators have to be the same. So 5 milliliters goes on top, and 100 milligrams will go in the denominator. Cross multiply. 100x is equal to 625 divided by 100. X is equal to 6.25 mLs. Okay? Now let's do problem number, let's go to problem number 21 and 22. So again, let me share what the book says. Let's go to problem number 21. Come on, computer. Okay, so here it is. It says, use the following label to answer questions 21 and 22. So we have zidovudine syrup. It says each 5 ml or 1 teaspoonful contains zidovudine 50 milligrams and sodium benzoate 0.2%, each as a preservative. So there's a 240 ml bottle. Okay, so let's go to the problem. So a patient is to take 12.5 milliliters of zidovudine syrup as shown. How many milligrams is this? So we know that 5 mLs contain 50 milligrams. Okay, and we want 12.5 mLs. So how much is that in milligrams? So let's go ahead and go to our whiteboard. So I'm going to write down what we know from the book. We saw that it's 5 mLs contains 50 milligrams of medication. That's what we have in pharmacy. What the doctor ordered is 12.5 milliliters. So our X value is going to be milligrams. That's what we want to know, milligrams. Okay? So X milligrams over what the doctor ordered, 12.5 mLs, is equal to, so again, we want milligrams on the top and mLs at the bottom. So looking at, we have in pharmacy, 50 milligrams over 5 mLs. Okay, so we're gonna cross multiply. And so 5x is equal to 12.5 times 50. Is equal to 625 divided by 5. X is equal to 125 milligrams. Okay, so that's number 21. Now number 22 is asking, a patient is prescribed 100 milligrams of zidovudine syrup as shown. How many milliliters is this? So now we know the milligrams, which is 100 milligrams. And again, it's the same dosing in the pharmacy, so it's 50 milligrams per 5 mLs. So our X value is mLs, okay? So X mLs over 100 milligrams, which is what the doctor ordered, is equal to, so mLs goes on top and milligrams will go on the denominator. So 5 mLs over 50 milligrams. So again, cross multiply, 50x is equal to 500 divided by 50. X is equal to 10 milliliters. Okay, so we'll go ahead and finish here. You'll have some problems from this section for homework. Again, if you need any help, please feel free to reach out to me and I'll go ahead and respond as soon as I can. Thank you, and we'll see you in the next section.